From last time, we're working with homogeneous differential equations with constant coefficients. And we said that we would let e to the mx be a solution, and then we found out that this turns out to be, for second order differential equations, this turns out to be just a quadratic equation problem. With a quadratic equation, we have three possibilities. We have the possibility that we have two real solutions. We have the possibility that we have one real solution. And then we have the possibility that we have complex conjugates. So, we got through the first two cases. In the third case, I think I'm just going to give you the solutions, and I started to talk about Euler's formula, but I think that's better discussed in a hours by arrangement worksheet. So, what we're going to do is we're just going to break it down to these three cases and then tell you what the answers should be. So let's take a look at the first case where we have two real roots. M1 and M2 are real numbers. Then your solution is going to be y is equal to C1 e to the M1 times x plus C2 e to the M2 times x. So e to the m1 and e to the m1x and e to the m2x are your two fundamental solutions. They're linearly independent because they are distinct. M1 is not equal to m2. They're two real distinct roots, and so they are linearly independent. And so the solution would just be a linear combination of those two fundamental functions. Now, the other one, we saw that we had one real root that technically is repeated, so that accounts for your two real solutions. But since they're the same, they're equal, we just say it's one real root. And we used the reduction of order substitution to find our second linearly independent solution. And so your solution for this turns out to be C1 times e to the m1 times x plus C2, and then the other fundamental solution is going to be x times that. So x times e to the m1 times x. And those two are linearly independent, so they would form your general solution for your differential equation. So the last one involves complex conjugates, and we started to talk a little bit about it, and then instead of going into more detail, I'm just going to tell you what happens. So the m is equal to alpha, I'll use alpha, plus and minus I times some other number beta. And there's some interesting complex number theory. It's not really theory, it's more like algebra, complex number algebra that's involved here, where you get to write this complex number as in polar form. But again, we won't do that stuff. What this turns out to be is, I'm just going to do an intermediate step here, which I think I kind of started to take last time. One of your solutions is going to end up looking like e to the alpha times e to the I beta and then I beta becomes, by Euler's, becomes sine and cosine, right? So this is what happened in our discussion last time. And what we can think, or how we can think about it, is that I, the imaginary number, although it's not a real number, it's complex, it's still going to be treated, or can be treated, as a constant. And so what do you really have? You really have your linear combination of e to the alpha cosine beta, e to the alpha sine beta. And so that's exactly what you're going to have as your solution. So your solution set will be C1 e to the alpha x, because this is multiplied by x. I didn't multiply it by x here, but this is multiplied by x. E to the alpha x times cosine beta x. That's one fundamental solution. The other fundamental solution, if you distribute that, is e to the alpha x sine beta x. And so these two are your fundamental functions, fundamental solutions, and then you string them together as a linear combination. You have your general solution for your differential equation. Okay? So let's do a couple more problems with a homogeneous section here, and then we'll move on to the next section. All right. So there's a bunch of problems to do here. Let's just take a snapshot of the problem set over here, and then randomly pick one or two or three. 2 to 14, even number? Pick a number. What? 8. Let's start off with 8, and then we'll do some more. So y double prime plus 4y prime minus y is equal to 0. This is your differential equation. Now, you can go through the steps of writing your solution as y is equal to e to the m times x, and then take the derivative and plug it in and do all that stuff. But, you know, we can really just pull out the auxiliary equation here, right? So let's just do that instead of going through all the motions of the other stuff. Let's pull out the auxiliary equation. What's auxiliary equation going to be equal to? M squared plus 4m minus 1 is equal to 0. Now, what are the solutions? Can we factor? Can we do something? We use, what's that? Pythagorean? No, quadratic. M is equal to -4 plus or minus the square root of, what is that, b squared? So 16 minus 4, a, c. C is -1, so that's going to change the sign here, and divide by 2a. And what do we get? We get -4 plus or minus, what do we get inside of the square root? What's our discriminant? Square root of 20 over 4 over 2. And we could take out a, what do you call it, right? A 4. So that's root 5. So this becomes -2 plus or minus 2 root 5. Yeah. So let's get rid of that too. Okay, so what do we have here? Do we have two real roots? Do we have complex conjugates? Two real roots, right? They kind of look like conjugates. There's no I here, so this is a two real roots parts. So what are your two? Well, let's just go straight to the answer. Can we? So y is equal to C1 times e to the first real root. What would you say your first real root is? Minus 2 plus square root of 5. And let's put that in parentheses times x. And your second fundamental solution, C2, e to the minus 2 minus square root of 5, and that whole thing times x. And here's your general solution. You're done. Okay? So all that theory that was built into that discussion last time really boils down to making our work really easy and fun. Let's do another problem. Which one? 14. Number 14, we got 2y double prime minus 3y prime plus 4y is equal to 0. Okay, let's jump to our auxiliary equation, which is going to be what? What? 2m squared minus 3m plus 4 was 0. Now suppose we can factor this. We have to use a quadratic equation again. We're going to get complex here, huh? So negative 3 plus and minus the square root of negative 3 squared, let's just call that 9, minus 4 times a times c all over 2a which turns into 3 plus and minus square root. What goes in here? Square root of what? Negative 23. Not only is it complex, it also is a big mess. So if we want to see the I pop out of here, you can put the split up the fraction and we get to see the complex number. By the way, I don't know if I talked about it last time, but the part of the number that's next to the I is called the imaginary part. And the part of the number that goes that's not with the I is called the real part. So any complex number has a real part and an imaginary part. So if you remember back with the alpha and the beta as a complex conjugate roots that we found, this real part will get attached to an exponential. The imaginary part would get attached to the sine and cosine. Remember that? So we can immediately jump to our solution. Y is equal to, the first fundamental solution is going to be multiplied by C1. The first fundamental solution is going to be e to the 3/4 x times cosine. I guess it doesn't matter if sine or cosine, but I'm usually like to put cosine first. Cosine root 23 over 4 times x. So that's the first fundamental solution. The second fundamental solution multiplied by C2 is almost the same thing, except instead of a cosine, you're going to get a sine. So e to the 3/4 x times sine root 23 over 4 times x. Okay? All right, I'm not going to do a third example, but if you had one real root, then your second fundamental solution will have an x to it multiplied as a factor. So that's all we need to really talk about for homogeneous differential equations. Questions? All right. There would normally be an I next to the sign one when you were to write it out at first, but since we are just looking for the solutions to the differential equation, that I is a constant, and so we can. You can think about it as being absorbed into the C, or you can think about it as a fundamental solution that's linearly independent. So with fundamental solutions, we usually chop off the extra constants that are laying around. All right, any other questions? So we do want, since our differential equation is living in the real world, we want real answers. And by real, I mean not complex. By complex, I mean not hard or difficult, just complex with an imaginary number. Now it's all confusing, right? Okay, are we good? All right, so this is our foundation to go to the next level, which is to consider non-homogeneous differential equations. Actually, before we go there, let's extend our homogeneous differential equation idea a little bit further. Jumping the gun here. So we all know the fundamental theorem of calculus, right? I mean, if we know it, great. If you don't know it, you've at least heard it before. So it turns out that there's a fundamental theorem of arithmetic also, and then there's a fundamental theorem of algebra. And the fundamental theorem of algebra states that whatever power your polynomial is, and this is dealing with polynomials, you're going to have that many solutions, roots, when you set that polynomial equal to 0. Does that make sense? If I have something to the third degree polynomial, then I'm going to have 3 roots. If I'm going to have something to the 10th degree, my polynomial is a 10th degree polynomial, I will have 10 roots. Maximum, exactly. Not at maximum or minimum, but I will have exactly 10 roots.
Because you can have like a second degree polynomial and have no roots.
Right. Well, when I say roots for the polynomials, we'll have n roots that deal with the complex plane, and also counting multiplicity. So those 3 cases that we had for the second degree polynomial, one of them counts multiplicity, the other one is in the complex plane, or in the complex world. So regardless of what your polynomial is, you're always going to be guaranteed to have as many roots, exactly as many roots as you do your degree. Okay? So if we take a look at x to the 10th minus 1 is equal to 0, I will have 10 roots here. I will have 10 solutions. Now, you guys have all been living in the real world, so you guys are just looking at one solution, right? So x equals 1 is your solution. But if I'm supposed to have 10 solutions here, oh, also -1, right? If I'm supposed to have 10 solutions here, I should have 10 solutions. I only have 2, so I'm missing 8 solutions. It turns out that those other 8 solutions are complex. Okay? So if you ask Wolfram alpha, or since I have Mathematica, I'll just ask Mathematica. to solve for that equation that I had, x to the 10th minus 1 equals 0, and I'll solve for x, I should have 10 answers. And in fact, I do get 10 answers. Those aren't very nice answers. Arrow means those are your results. So x is equal to -1, x is equal to +1. Those are the two answers that we got. But then there's these other ones over here. The fifth root. I don't know. Why is it the fifth root? Let's ask Wolfram alpha. I think it gives us more information. Solve x to the 10th minus 1 is equal to 0. Solve for x. So these they make this a little bit nicer because they actually write it as complex numbers. So you have a bunch of complex numbers here. Have you guys seen this? A picture like this? This is called the roots of unity. Roots of unity. That when you actually have something to some power, you're going to have that many roots, and those roots are going to be around, spaced out evenly in a unit circle on a complex plane. Now, what's this unit circle in the complex plane I'm talking about? I'm going to assign that as an HBA eventually, so you guys will get to dig through that stuff. But if I change this to 4, I would kind of get the same picture. And those are my roots of unity. My answer for the fourth root, or x to the fourth, is -1 is equal to 0. Will come up to be positive and -1 and positive and -I, it turns out. And then if I change this to an odd number like 9, then I will end up having 9 roots of unity. One of them is x is equal to 1. The rest are all going to be complex. Okay? So the more popular ones that you guys know of are the x squared and x cubed. When you see x cubed over here, we think our solution is 1, and that's our only solution. But there are 2 more solutions that you're not hitting, and these are the other 2 solutions over here that are complex conjugates. So point being, when you have an nth degree polynomial, you will have n roots if you count multiplicity and complex roots. Okay? And if you just use this information, that if you have multiplicity, then you just multiply it by something else, multiply it by x. And if you have complex conjugate roots, then you have 2 fundamental solutions. So is that making sense? Let's see if it makes sense. Let's go to this idea and make up let me make up a differential equation. Let's just keep it simple at this point. Let's go with a third order differential equation. And let's do our regular assumptions. We'll assume that y is equal to e to the mx is the solution. Now let's pretend that we're going to take the derivative 3 times and plug it into this equation, and then we'll factor out an e to the mx. And what we're going to get here is basically the auxiliary equation. So it'll be m to the 3rd power minus 1 is equal to 0. You see how we got the auxiliary equation here without doing all the tedious work? So your solutions, looks like it's just m is equal to 1, right? But then we have to find those other two solutions. So aside from using Wolfram alpha, how else can we find the solutions? Oh, how are we going to find the solutions? Well, we can't use a quadratic equation. Uh-huh. You guys remember long division or synthetic division or one of those divisions? So if I know this is a solution, then I know m minus 1 is a factor. So I can write this as, let's do long division. M minus 1 goes into m cubed, 0m squared, 0m minus 1. So I ask myself, what am I going to multiply m by to get m cubed? And then, so I need to multiply that by m squared. So m cubed minus 1 times m squared. I subtract, this becomes a positive m squared. Remember that? What do I need to multiply m by to get m squared? I need to multiply that by positive m. Oh, I need to drop the 0 times m here. So this would be m squared minus m. Subtract that, this becomes a positive m again, minus 1, and so this is going to be just 1. So now if you find the solutions for this, you'll see the quadratic formula business again would work for you. So m is equal to negative 1 plus or minus the square root of 4, or 1 squared minus 4ac all over 2. So this becomes minus 1/2 plus or minus. This is going to be a negative 3 under the square root. So we'll just call it an I root 3. So I have one real root, I have two complex conjugates, so that's 3 solutions. And that matches with my order, so I know I have everything. So our fundamental solutions should have these things as e to the power, except when you have complex conjugates, you know that we're going to need to expand that. Right? So from here, you're going to get a solution of e to the 1 times x, right? E to the mx. And from here, you're going to get 2 solutions, e to the negative 1/2 x times cosine root 3 over 2x plus sine root 3 over 2x. And again, since we're going to put this into a linear combination of fundamental solutions, there's 2 fundamental solutions here, right? Since we're going to make this into a linear combination of fundamental solutions, we can just ignore the constants, including the imaginary number. So from here, we can get our general solution, and it's just by the superposition principle. We can just add them all. C1, e to the x, plus C2, e to the 1/2, negative 1/2 x, times cosine root 3 over 2x. plus C3 e to the negative 1/2 x sine square root of 3 over 2x. Yeah, the I in front of the sign, when we're looking for fundamental solutions, we don't consider the constants there, because that constant will just blend in with the general solution constants anyways. That's one reason to think about it. Another reason is that we are going back to the real solutions. Our differential equations were real, so our solutions should also be real. Okay? This is just solving for polynomials that are bigger than second power polynomials. That's really what it comes down to, except you're going to want to make sure you keep track of your complex conjugate solutions. Nah. Yes? Yes. For these homogeneous differential equations, when you have imaginary numbers, you use sine and cosine. Okay? Anything else? Can we do another problem? Yeah? Yep, there's just C1, C2, and C3. This is a general solution for a third order differential equation, so we need 3 parameters. Anything else? Yeah. Yes. Then you have to look. If it's equal to something else, then we do something else in the next section. Yes. All right. And here are some examples from the book of higher order differential equations between 20 to 28. You guys want to pick a number? Like 27, really? We can pick 27, I don't care. 27 is actually interesting. 25 or 27? Let's do 25 and then let's see what happens. So 25 is a fourth order differential equation. 16y quadruple prime plus 24y double prime plus 9y. All right. Again, we start off saying e to the mx, blah, 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 and come to the auxiliary equation. So auxiliary equation, I think it's going to be 16 m to the 4th plus 24 m squared plus 9 is equal to 0. Oh, can we factor this? Looks like it should be factorable. 4 and 3, maybe? You think? 4 and 3? Let's see. 2 times 4 times 3. What? Can we factor this is my question.
4m squared plus 3m squared.
That's what I was trying to say when I said 4 and 3 and 2 times 4 times 3. So it looks like we're going to have double roots. And inside here, remember that you're looking for 4 roots, right? So inside here, we're going to get, let's see, m is equal to -3 over 4 under square root. So this is going to give us complex numbers, right? So this would give us I root 3 over 2. Probably positive and negative or something, right? I'm looking for 4 roots. Let me just list down the roots here. I see that one of my roots is I root 3 over 2, negative I root 3 over 2. What are my other 2 roots? What? They're multiplicity 2, right? So my other 2 roots are I root 3 over 2 minus I root 3 over 2. So those are my 4 roots. You see that, the multiplicity? So I have both multiplicity and complex numbers. So this thing, the 2 roots that we found here came from in here, right? But then there's multiplicity of 2, so each of them is happening twice. Just like if you have x minus 1 quantity squared equals 0, you solve for what's inside, but then it happens twice, so you have 2 of those roots, you count them twice. So your roots are here 1 and 1. Your roots are 1 with multiplicity 2. Here you have 2 roots that's being counted twice, so these are your 4 roots. You got 4. Okay. Now, if we're dealing, remember, if we're dealing with complex conjugates, your solution is going to be we need 4 fundamental solutions that are linearly independent. And let's start off with thinking that we have complex conjugates as our roots. So your solution will be e to the, what's the real part of this root? Real part of the root? 0. So e to the 0 power, so we don't count e to the 0, right? So it'll just be cosine root 3 over 2x and sine root 3 over 2x. So if we have complex conjugates as our roots for our auxiliary equation, then our fundamental solution would be a combination of sine and cosine. And instead of having an e to the 0 here, which is what we should do, e to the 0 is just 1, so I'm not even looking at that. So now, with our second set of roots, because it has multiplicity, it wouldn't really make sense to write the same thing again, right? Because the same thing would be linearly dependent. This is wrong. No? If you square it, remember, I think sine squared and cosine squared are linearly dependent from each other. Or if you throw in an extra value. So how can we make sure that we get linearly independent values or solutions? One way to do this is, I'm not going to go through it, but one way to do it is to do the reduction of order. We'll have to do the reduction of order like twice and then see what we come up with. I think that's a little bit of a headache. But let's go back and see what happened when we had multiplicity. If you had a repeated root, what did we do? We just multiplied it by an x, right? And if you multiply it by an x, you get something that's linearly independent. So that's exactly what we're going to do. We're going to take these two solutions that we got that are linearly dependent from the other two solutions that we got, and then let's just multiply it by x. So x times that, and now they're linearly independent. All four of these solutions are linearly independent. You can use a Wronskian to check this. And now we have four linearly independent fundamental solutions for a fourth order polynomial. So this will just be, your general solution is just be a linear combination of all of these. So then your y is going to equal to, I don't want to write it down. I suppose I'll write it, I could. C1y1 plus C2y2 plus C3y3 plus C4y4, where your y1, y2, y3, and y4 are all these functions. Gets to be a little long, huh? Yeah, I guess, if that's what they asked you in WebAssign, just type all that stuff in. Okay. So there are probably lots of questions. I think right around this point I started to see some glossy looking eyes and lost faces and stuff. Can somebody ask me a question at this point? Would that even work? No. This has nothing to do with the quiz. No. Yeah? Yeah, so that's the other thing, is that if there's multiplicity more than 2, you just make it an x squared. In fact, we might as well talk about number 27. Two, that blows everything. It's negative. What? I'm going to cheat here. Or something like that. Oh, this has multiplicity of 2, so let's not do this one. Sorry, I'm going to change the problem to, let's just say, I don't know, it's hard to think about it like this. Let's just say I have m minus m minus 1 to the fourth power. Okay. So m minus 1 to the fourth power. What's the differential equation if I expand this? How do I expand this, by the way? Yeah, but I want to actually multiply everything out. So if you guys remember your Pascal's triangle, right? Let me get rid of this stuff. So I would go backwards. This would be m to the fourth minus, what are those numbers in Pascal's triangle? 4, m cubed plus 6, m squared minus 6, m plus 4.
Minus 4m.
Oh, this is minus 4m, and then this is 1. So your corresponding differential equation would be the fourth derivative minus 4 times y third derivative plus 6y double prime minus 4y prime plus y is equal to 0. There, we just came up with an example. So your solution here is m is equal to 1, and it has multiplicity 4. So 1 4 times is your solution, or it's your solution for this auxiliary equation, which means if we want to make a list of your fundamental solutions, you need 4 of them, right? So the first one is just going to be e to the mx. And had this been a multiplicity 2, we just find our next solution would be x e to the x. And so if you have more multiplicity, a higher multiplicity, and you could, technically what you would do is you would use the reduction of order formula, but in this case you would just, if you were to do the reduction of order formula, you'll see that your next solution would be x squared, and then your other solution would be x cubed times the original fundamental solution. And so you string this up as a linear combination, then you have your general solution. Okay? So if you have more multiplicity, just throw in an extra x in there. All right. Doesn't look like we're going to get to non-homogeneous differential equations, so I think this is enough to chew on for now. So you guys want your test, huh?